Today's lesson is exponential and logarithmic growth and decay. My learning objective is I can generate and solve exponential and logarithmic equations by using the exponential growth model and inverse properties. Let's take a minute to see where we are on the learning curve. If I've never heard of this before, I'm a novice. If I remember everything from Algebra 2, I'm an expert, or I'm an apprentice or practitioner in between. So lots of processes that occur in nature follow a certain model. Some of these can be radioactive decay, heat diffusion, a virus, COVID-19 maybe, bacteria. Others can be modeled by using this exponential function. So the model is n of time t equals n of sub 0 e to the rt, where e represents Euler's number and it's approximately 2.718. N of t is the value at time t. N sub 0 is my value at t equals 0, my initial time. R is the relative growth rate, and I say that as a percent, but I use it as a decimal in the equation, and t is time. All right, let's do some examples. All right, the initial bacterium count in a culture is 500. A biologist later makes a sample count of the bacteria in the culture and finds that the relative growth rate is 40% per hour. Find a function that models the number of bacteria after t hours. All right, so let's start labeling everything here. My initial bacterium is 500. So this would be n sub 0 at t equals 0. And my rate is 40%. So 40% as a decimal is 0.40. So my equation, so my model is n of t equals n sub 0 e r raised to the power r times t. So substituting in, n sub t equals 500 e to the 0.4 t. Okay, next question. What is the estimated count after 10 hours? So t equals 10. Oops. So t equals 10. So n at 10 equals what? So n at 10 equals 500 e to the 0.4 times 10. So in the math world, we usually round 3 decimal places. So if when I put this in my calculator, and I have a button that has E on the calculator. So in the math world, what I would say is this is 27,299.075 bacterium. Because I round 3 decimal places when I'm talking about exponential or logarithmic. But in the real world, I can't have a partial bacterium. And I don't round up for 0.5 or above. I can't have a whole if I have a partial one. So in the real world, the rounding would be 27,299 bacterium. So the farther you go in math, the more you have to understand, is the answer expected as a mathematical answer or a real world answer. Okay, next question. How long until there are 50,000 bacterium? So how long is, what is the time where n of t equals 50,000? So this is n of t. Okay, so my answer is 50,000 equals 500 e to the 0.4 t. Okay, so I have an exponential equation. My variable is in the exponent, and I want to solve for the variable. So I need to undo the exponential equation. And I do that by taking the inverse, which is a logarithm. But I can't do that until I have a 1 before the base. So the base is e, and I need to have a 1 before the base. So I first have to divide by 500. Oops, I put 5,000. So I want to divide by 500 first. So I get 100 equals e to the 0.4 t. So now that I have a 1 in front of my base, and my base is e, so I am going to take the logarithm of base e, which is called natural log. So I'm going to take the natural log of 100 equals the natural log of e to the 0.4 t. So the purpose in that was the natural log of base e becomes 1. These two undo each other. So I have the natural log of 100 equals 0.4 t. So next I want to divide by 0.4. So I get t equals approximately, so not equals. T is approximately 11.513 hours. So I'm always rounding 3 decimal places unless I'm told. All right, let's try one more. I don't have too many of these to practice. We've been working on pretty many of these. A certain breed of rabbit was introduced into a small island about 8 years ago. The current rabbit population on the island is estimated to be 4,100 with a relative growth rate of 55% per year. What is the initial size of the rabbit population? All right, so I'm going to start out with that this is talking about 8 years ago. And this 4,100 is n of 8. So I'm trying to find the initial size. What's the initial size? So that's n sub 0 is what I'm trying to find. So the 4,100 is 8 years later, so that's n at time t equals 8. And my rate is 55%, so as a decimal that is 0.55. So my equation, n sub t equals n sub 0 e to the rt. Substituting in n sub t is 4,100 equals n sub 0. E, my rate is 0.55, and t is 8. So to find n sub 0, I want to divide by the coefficient next to it, which is e to the 0.55 times 8. Whatever I do to one side, I have to do to the other side to keep it equal. So I find out, so this is 1. So n sub 0 equals 50.337 rabbits. And clearly this is a math answer. All right. In the real world, I'd say it was 50. Okay, next question. Estimate the population 12 years from now. So we can do this more than one way. So let's try one way. First way, and these are easier if you kind of draw a timeline. So at t equals 0 and t equals 8. So this is now. And it's asking me 12 years from now. So that would be t equals 8 plus 12. So t equals 20 is what that's asking me. So t equals 20. So at t equals 0, how many rabbits do I have? So at t equals 0, we're saying I have 50.337 rabbits. Right now, I have 4,100 rabbits. And I want to know here at n sub 20, how many rabbits do I have? Okay, so I would set in my equation, n of 20 equals 50.337, because I want to use my initial amount, e to the 0.55 times 20. When I put this in my calculator, I get 3 million. I get 3,013,890.276 rabbits. Okay. That's one way I could do it. Another way I could look at the timeline is I could look at it where I'm saying this is, the now is t sub 0 and 12 years from now. But when I'm saying t sub 0 is here, my rabbits, the n sub 0 is this 4,100. And I'm looking for n at 12, not n at 20. So I just need to know what my 0 is. So solving for n of 12, where n sub 0 is 4,100, e to the 0.55, and t is 12, I get exactly 3,013,890.276 rabbits. So sometimes I can do these more than one way. I don't always have just a single way to do it. And I find it easier to sketch out, anytime I have timelines, sketch out a timeline.